Okay. Perfect. Okay. Okay. Hello. I'm Kike. I'm from Cornell doing a postdoc there, and I'm going to talk about spectral methods for space physics using Daedalus. It's going to be it will have a flavor of a tutorial. So first, this is the contents of the talk. I'm going to talk a little bit about spectral methods and specifically Daedalus, which is the library I'm using. It's an open source Python library. And then I'm going to apply this to various like toy problems at different regimes that are relevant for space physics, kinetic phenomena, fluid phenomena, and what I'm calling here nonlinear reduced models, which is probably not the best label, but that's the one I'm using. So as you probably know, the general recipe to solve a partial differential equation like this one, like a diffusion type of equation, is to discretize the derivative, is to approximate the derivative. And that's fine, and that has been used when it works, it works. So, but there are some other alternatives. So for example, here I put paragraphs from the Bible, the numerical recipes from President Tucholsky, and they they basically said that if you can use the spectral methods, use them. That they are very good at converging, they converge exponentially. If the solution is smooth, you can, the convergence can go exponentially, but it's only optimal for simple geometries with a periodic, for example, with periodic boundary conditions. And the general philosophy of this is that instead of approximating the derivatives to finite differences, you approximate the solution like this. You say that the solution is a superposition of basis functions times some coefficients. So for example, if you consider the wave equation there, because it's you can decouple that in order to have it the first derivative on time, you can write this system of equations at this form, like in operator form, like a linear operator form. But because the solution has been assumed to be a superposition of coefficients, and you can operate analytically on each of these bases, you can transform this operator form to matrix form. It's a linear operator. And then you can make this system evolve. This is going to be the general form of this system. So how does this look in Daedalus? For example, let's say that you have a general convection advection reaction equation like the top one with constant coefficients. So first, what you do is you initialize the problem. You say what geometry, what basis you want to use. Then you say, I want to solve an initial value problem. I want to use these parameters. Then you add the equation this way, like almost in a LaTeX type of way. And then you choose the time stepper. So how you are going to evolve the coefficients in time. Then you initialize the system and you make it evolve in a loop. Everything is manual. There you can see an example of how Daedalus do compared to Athena, for example, which is a very sophisticated simulation. You see the grid size of Athena is very large, and the one of Daedalus is very small, and they can more or less capture the same physics. And I think that it seems to me that a big fraction of the problems in space physics are very good for these kind of things because they usually have some damping mechanism, some collisionality, and also usually there are not a lot of shocks, and the boundary conditions are pretty simple usually. So I'm going to use this in a couple of things. So first, I'm going to use this this is a very well-known problem. This is the Langmuir waves. And to capture the Langmuir wave, you have to solve Poisson equation. Here, this is Poisson equation, potential, and the density. And this is the Vlasov equation. So in order to solve this, I'm going to choose two bases. I'm going to choose Fourier basis in this direction, which can be considered periodic, and a Chebyshev basis in this direction, okay, because I want this to decay because this is the velocity dimension. And that's why you see that the grid is not equally spaced. And this is the initial distribution, which is the Maxwellian times perturbation. And this is how it looks at Daedalus. For example, this equation here is Poisson, and this equation here is Vlasov. And here you put a condition to say that the zero mode of the potential is going to be zero. And if you make the system evolve, you see this is the density perturbation and its time. And you see that there are some oscillations there. And if you take the Fourier transform in the spatial direction, you're going to see the only mode that we put, and it's going to decay. And when you plot the time series of the electric field amplitude and compare it with the analytical solution of lambda damping, you're going to see that there's a pretty good correspondence there. And that works fine. So an example problem that I chose was the exosphere distribution, the distribution of the exosphere dynamics. So as you probably know, in the exosphere, there's this issue with the Knudsen number. It's so large that you can't use fluid models. So you can use, you have to go kinetic. And for example, you can solve the Vlasov equation with the acceleration term proportional to the acceleration of gravity. So what I'm doing here is I'm going to use a distribution function of the hydrogen atoms that is going to have a Maxwellian component that decays with radius plus a perturbation. And I'm going to use Dedalus to solve for the perturbation. So in this case, again, I'm using now a velocity, a Fourier basis in the velocity space and a Chebyshev basis in the radius. So Fourier basis is usable if you have periodic boundary conditions. But in this problem, we don't have periodic boundary conditions in the radius. So for that, we use Chebyshev. And this is the equation that we are solving. The equation, this is Vlasov, and this is an auxiliary equation I'm using. So I put these substitutions here because you can see that this term here is, has a very long form, but Dedalus allows you to compress all of that like this. And you can add boundary conditions. So for example, here what I'm saying is that the derivative of the distribution function at the end of the grid has to be constant, has to be 0. And this is how the grid looks. This is how I'm initializing the system. When I make the system evolve, it looks something like this. Here you see the perturbations evolving in time. This is the total distribution function. So the particles here, they're going back to the Earth, and then most of the particles are going to locate near the escape velocity. Here, I'm not using any collisionality close to the exobase, so that's why the particles are centering in the escape velocity. So now we're going to go to a different hierarchy. We're going to model fluid things. So in this case, the toy problem I chose was the fluid, 5-moment fluid system, and for a plasma. So these are the continuity equations, momentum equations that can be solved for both species. And actually, I should have a Poisson equation here for the field, the electrostatic fields. So how does this look in Dedalus? So these are the equations that I'm solving for the potential, for the ions, and the electrons. And as you can see here, the electron, for example, they have this continuity term. And this is just a variable, in namespace that accounts for all of these operators here. And you can see the operators can also be introduced in a latex type of form. Wrong order. So if you make the system evolves, you will see this. This is the electron density and ion density oscillating, and the velocities there doing their thing. And apparently there's not much things going on, but if you take the Fourier transform in the x direction, if you just take, slices here and make these slices evolve in time, you're going to see this. So you will see some waves moving around. If you take the Fourier transform in this direction, you're going to see the wave components, how they vary in time. And if you take the Fourier transform in the time direction, you will see that the wave modes, they are very close to the analytic dispersion relation. And the quantities there are the conservation quantities. You see that the density is perfectly conserved. Energy is pretty good also, and the momentum as well. It has some oscillations there, but they go to constant very quickly. And the reason there is this decay is because I initialize this with white noise. So there is like a transient, and then the system relaxes and it goes then to well-behaved. So then I'm going to apply this to the Farley-Buneman instabilities, which is a more realistic problem. And as you know, the Farley-Buneman instabilities, they arise basically because the collisionality between the electrons and the ions in the A region is different. So there's this current that triggers the instability, that makes any perturbations here in the plasma grow and grow. And the linear theory for the fluid model tells us that the smaller the structures, the faster they are going to grow. Okay. So, and how does this look in experiments? If you point your radar in the direction of of these irregularities, you're going to see that they have a very well-defined Doppler shift, very small spectral width, and this Doppler shift is going to be more or less at the ion acoustic speed. So if you want to solve this with a fluid simulations, you have to be careful because, as I just mentioned, the fluid dispersion relation tells us that the smallest the structure, the quicker it's going to grow. So in order to account for that artificial growth, you model this with kinetic physics, because Landau damping takes care of this growth. But we want to simulate this with fluid systems, so we need something to kill this growth of a smaller scale structure. So what we are going to do is we are going to solve the finite moment fluid equation, but we are going to add a regularization term R. And this term R is informed by the work of the people at Princeton. They have figured out some proxy for the Landau damping. I'm not going to go into the details there. But the funny thing here is that this operator, I don't know if you see the exponent of that differential operator, it's a fractional. So this is a fractional Laplacian, and this is like a whole different field. There's a lot of literature of the interpretation of that. And when you want to solve this in physical space, it's very challenging because you have to solve a Hilbert transform at every iteration. But in spectral space, this is trivial. It's just like a filter. And sorry, I think I messed up the order. Okay, so how would this look like in Daedalus? It's basically going to look like the electrostatic wave that I showed before, but also there's this Landau proxy, it's a collisionless closure, Landau fluid operator. And then I put this in the energy equation like this. And also I added this chunk of code to show that in Daedalus you can very easily make diagnostics. So you say you create an evaluator that says, okay, I want you to create an HDFI file in this direction, and I want you to sample these variables here every certain amount of iterations. And these things can be very complicated. It can be integrations of the field, cuts of different things. So, and if you do this thing correctly and use kinetic methods, you're going to see something like that. That's the electron density, and it's going to evolve like that. That's from Oppenheim 2008. So I use the code that I just showed to simulate that with similar parameters, and this is what I got. So here you're going to see the electron density. This is the power spectra. This is a cut of the electron density perturbations, a time series of some parameters. And that is going to measure the amount of growth. It's going to be a proxy for the amount of growth of the instability there. And you see here similar patterns to what you see from the peak simulation. And yeah, that looks pretty cool. And then it dies because I turned off the background electric field. Just one more time. So it's growing, the electric field is starting to trigger the instability. And these are meters. And then it gets to a peak of growth, and then it's turbulent. That means that secondary instabilities are being produced all over the place, and then the field is killed and the irregularities decay. So now I'm going to explore what I call these nonlinear reduced models. And one toy model for this is the nonlinear Schrödinger equation. And the nonlinear Schrödinger equation comes up in several places. I'm not going to go into that right now. But I like this example because it's a complex partial differential equation, and also because it's a good example to show how the bases can be combined. So for example, if you want to use Daedalus here, and you want to use a Chebyshev basis because these are not periodic boundary conditions, and you know that in the center you need more resolution, then you have to make a tweak there, because Chebyshev has an agglomeration, a clustering of points in the borders. So if you want a clustering of points in the center, you couple two Chebyshev bases to have more points here. And this is how you do it in Daedalus. And you just put like the complex numbers inside the fields. That's nothing for a spectral method. It's complex by default. And if you make the system evolve, you are going to see here the real and imaginary component oscillating here, and here are the errors with respect to the analytical model. It's actually the relative error, so it's a very small error. And it oscillates and it's doing fine. So a realistic version of this is the, a realistic version of this system would be the Sakharov equations. And the Sakharov equations come up with when you decouple the fast and slow timescales in when you force Langmuir waves to start like growing and growing and decay nonlinearly. And this happens a lot in heating experiments, for instance. So as you maybe notice here, if the electron density is gone, then you recover the, if the electron density, if the density, plasma density that is constant, you recover the nonlinear Schrodinger equations. And here I'm showing some examples of what you should get if you solve this correctly. So in this paper, I think they use finite volumes, if I remember correctly, finite volume discretizations. So now what I'm going to show here is the example of how this is looking there. This looks in Daedalus. And now I am showing what you get with two different time steppers, Crank-Nicholson and Runge-Kutta. And you see that the evolution is very similar here in both cases. The density and the electric field is very similar to what I show from the paper. And in the other column, you see the errors between these two time steppers. So this is just to illustrate that it's very easy to just change the way that you are evolving the coefficients of the spectral methods, of the spectral decomposition. You can use different time steppers, and you can even build your own. Yeah, sorry, I'm about to finish. Okay, and I wanted to add that this, I saw this GRL paper that simulates Lamb waves, and it made a very, it is an extra slide. This made a very interesting argument. I wasn't aware of this, that if you take the system of that reproduces Lamb waves in 3 dimensions and you integrate in altitude, you basically get the shallow water equations. And in the paper, I think they claim that the dispersion relation of these two things is the same. So these are the equations of shallow water equations in a spherical shell. And these are some of the simulations that they got. This is satellite data and simulation. And they use a very sophisticated simulations with from a global model for the oceans, I think. So these are the viscous shallow water equations because they have these viscosity terms there. So I use this Daedalus, and I wanted to illustrate the versatility that it has to solve different geometries. So this is solved in a spherical shell. I put a perturbation here, and I simulate these 2 points, P1 and P2, which would be like sensors. And you can add that as diagnostics, and Daedalus is going to measure the perturbations at those points in the grid. And I don't know if you can see this, but there is like a wave that is going back, this wave here. I was very afraid that there was a problem with the code, but it's actually that the sphere is transparent, so there's no problem there. Yes. So, oh, and something else. This is these are already optimized to run in parallel. So this simulation took like 3 minutes, I think. Most of the simulation, all the simulations that you've seen here took less than 20 minutes, with the exception of the Farley-Buneman one. That took like 5 hours, I think, something like that. On oh yeah, parallel in your computer, your desktop, yeah. If it has several cores, I don't remember. Different simulations use different amount of cores. I don't remember exactly, but we can talk about it later. So this is a summary. Spectral methods are probably very useful for plasma physics, space plasma physics, because the solutions are very smooth and the periodic boundary and the conditions are maybe similar, simple enough. And Daedalus is pretty versatile to solve these kind of PDEs. Yeah. And if you want to know more about the Farley-Buneman simulations, you can go to these sessions here. I'm going to talk about that in more detail. Mm-hmm. Yeah, that's it. Thank you.
So in computational methods, I saw you look where are we at?
So one of the
there we go.
One of you have to sacrifice efficiency for versatility, as you know. Nevertheless, I would say that the Farley-Buneman, for example, the Farley-Buneman simulations that I just show, they're just an example, and I have tested, for example, boxes of 1 kilometer and 500 meters, and that runs in 5 hours using 64 cores, more or less. So it's still very fast.
So is this parallelized then?
Oh yeah, Daedalus is parallelized by default. Yeah.
By default.
Yeah. So you can run that with in the terminal. You just add MPI exec and specify the number of cores, and that's it. Yeah.
So that does help. But it is still an interpreter.
Well, it's built on functions that are written in Fortran and stuff. So for example, they use yes. So it's like it builds the how do you say this? It's on top of the SciPy Fourier transform, for example. That's one of the most important things. Even if for the Chebyshev polynomials, they build the spectra using fast Fourier transforms and stuff like that. So yeah. Mm-hmm.
Very impressive.
Okay, thank you.
And there are some chairs up here in front. Those just showing up. I can bring it back. All right. Making progress. Happy. All right. Okay. I want to thank Russell for inviting me to give this. This is a great opportunity. This is a very different kind of talk than we just heard. This is about kind of infrastructure and underpinnings, things that we're doing in the heliophysics data environment to try and make data access easier. So there was a data session a few days ago, and Ryan McGranigan mentioned something about hidden infrastructure. That's kind of what this is hoping to become, or it's partly becoming that. So happy. It's the Heliophysics Application Programmers Interface. I'm sort of representing the whole team here. There's people from many different institutions that have been working on this. So here's the rough outline. What is HAPI? Why should I care? And then how to use it if you're trying to analyze data or if you're trying to provide data. And then a few comments about what's coming. All right, so first, what is HAPI? The prelude to that is what is time series data? Because HAPI is an interface for accessing time series data. And so I just thought I'd mention that at the beginning. It's just any kind of tabular data that you've got time column and then data columns. And almost all of the CEDAR archive at Goddard for heliophysics non-solar data has data like this. a lot of data in Madrigal, ground-based magnetometers. There's many, many data products that have this sort of structure. So even though we have heliophysics in the name, heliophysics application programmers interface, there's nothing actually heliophysics specific in the API. And the data,
Hey, John, we
Yes?
can't see your slides online. Could you share your screen?
oh,
That
yeah.
would be great.
Yeah, we're gonna pause for a second. And thanks, Rebecca. Share screen. Okay, and then we do full screen. Hit the play button. All right, yeah. Keep it. How's that, Rebecca?
Friends.
This meeting is being recorded.
Okay, can you hear us again?
Yes.
We lost our internet, but we think we're back. And can you see the screen?
No.
No.
We said share, but maybe the interrupted internet killed our share. Yes, it did. Share screen here, play.
There you go. Thank you.
Okay,
That
so
works.
we were about here, interoperability. Yeah, the same piece of code to get data from lots of different places. And the whole point is to just kind of impedance match that, you know, what the data is coming from with the analysis that you're trying to do. So how do we simplify access? So we'll kind of step through this, and if everybody knows about this process, but there's a data provider, they have a custom data interface for requesting data. So you write some program that can grab that data and then you pull it into your code. So the problem is you'll have to do that for each of the different data centers because they've all done it slightly differently. And so we're saying that we're not saying that you should replace that, but you can supplement it with a sort of generic version of that interface that everybody agrees to. And that way, if you go to talk to other providers, you're talking to them with the same interface. And so when I say a simpler version, we really aim for a lowest common denominator approach. So it's brain dead simple. You want to get time series data, tell me what your data set name is and what time range you want. That's it. And so, you know, you can, if it has 60,000 parameters and you only want 100, you can just list out the ones that you want. That's optional. Okay. All right. So what is happy continuing here? It's a specification. So that's a language independent thing. It just describes on the server, what is it that you have to do to provide data. So it's defining a kind of a protocol. And we have servers that we've created so far in specific languages like Python. And a lot of the focus of the development has been in the Python community, which is why we're in the Python session. But there are other languages available too. Oh, and back on it's being a specification. The fact that that request interface is so simple, just data set and time range, it means there's no data set specific parameters that you can put on there. So it's really just meant for accessing data this is it. I prepared the data and here it is. A lot of sites will offer things like, well, do you want background subtraction or do you want, you know, nighttime data or daytime data or whatever. It's like, no, that you have to just provide the data and this lets you access it. If you have decisions to make, you know, you still would need the custom interface. And this is kind of pushing people to say, look, make the data available so people don't have to decide, should I subtract the background, right? Or provide that in a different data set. Here's the raw, here's the background subtracted, because the team knows how to do that the best. And so providing that for people. All right, and then there's also clients available that understand how to talk to the servers and can pull things into the code and you can start using the data. I'll talk about that a little bit more. Don't read this. This is a reference page to have in the materials once they go online. I'll point out the two things with the arrows. Like I said before, it is a specification. We wrote that first, and that's what takes forever to get everybody to agree because everybody had all these bells and whistles on there and convincing people to cut things out. And then there's a nice way to explore the happy data servers that are up and running now. It's a kind of a JavaScript client that shows you, pick a server, hey, I'll show you what data is available, pick the data and so forth. And I'll say a little bit more about that in a minute. Okay, so why should you care about this? Well, it's back again to this problem about the data analysis workflow. Because suppose everybody wants the same thing. I wish every data set that I wanted to analyze was in whatever, Madrigal or in whatever your data system was. And so you found your magic lamp, you've got 3 wishes. And so that's your wish. It should all be in Madrigal. Well, the problem is every other data center person, every other person asked for it to be in their data set. So your wishes cancel out, and that's not going to happen. So you're down to 2 wishes. So now you can wish for that everything that you wanted to access was at least the same as the way that you did it for Madrigal. And so that means that if you have data, you write some data wrangling code, and it pulls it into the data structures inside your own code, and then you go off and do your analysis. And what you'd like for then your next wish is, ooh, I wish I could read this new data with the same way. And so you burn up one more of your wishes. Oh, but you still have 1 wish left, so you're good to go. Because Happy would let you complete this sort of fill my array mechanism because you've already written that data. You've already written that data wrangling code, and you don't have to do it again. So this is, if this really was present, it would revolutionize the way people do it, because you don't have to care about the file formats, you don't have to care about the structure of the data. You just say, I want this data. And it shows up in your code in the data structures that you can then carry on with. So this is an example that I pulled together quickly. There's a program called Autoplot that already knows how to talk to Happy servers. It lists out which ones are there. You pick the server, you pick the data set, you pick the time range, add plot, add plot, add plot. This came from all over the world, 5 different servers, and it just knows how to pull them in. You've got spectrograms, mag data, different kinds of things. So there's, do I show one? There's one that's an ephemeris server. It shows you where the spacecraft is. So you can get all of that using one tool. This is a little bit dated of a picture. Darren DeZeo did this work with data model comparisons. He's pulling the data from the CEDAR web archive at Goddard, and he's pulling the ephemeris data from the SSC web. He uses the ephemeris data to fly a spacecraft through his model, and he pulls out the model data at that ephemeris, and then he compares it with the real data from a measurement, and that's using Happy for both the ephemeris and the actual measurements. So, it's starting to enable some things like these comparisons and higher level analysis. So what if you want to, this moving on to the next part, what can I do with it? Well, if you are a data provider, sorry, this is kind of a boring slide, but again, kind of for reference material. There are servers out there that you can start using. There's a development group that's happy to help with that. We actually have a little bit of funding this year to go out and not only do things like this to tell people about it, but we can actually meet with you and help you get going on it. We've done this with ESA. They have a large heliophysics archive, and we've helped them set it up. That one's about to go live. So there's also a testing mechanism. Once you have a server standing up, you can point this testing mechanism at it, and it'll go through and hammer everything. Oh yeah, the verifier. So you literally just tell it, hey, here's my server, and it's going to go check everything. Does it meet the spec? And it's going to hammer it, asking for everything, checking that, and it's going to throw it some bad stuff and see if the error codes are right and all that. So, and it shows you red, yellow, green. Does it pass all these things? So it helps you get going. So that's great. Bob Weigel wrote this. He's done a lot of the work on this too. Should definitely give him a shout out. I mean, yeah, he's probably done more than anybody on this. Okay, if you want to analyze data, you're not a provider, but you're more into the analysis piece. Here's some different areas, different things you can do. Like I said, Autoplot already knows how to talk to Happy servers, so that one's good to go. The SpeedOS and PySpeedOS tools have been augmented with Happy data. And like I said, there's client code that exists where you don't want to use somebody else's application. You want to write your own application, and that's what most people do. So there's libraries to go ahead and grab the data. And this mechanism that lets you explore what Happy servers are available and what data is present there. You say, oh, here's the data set, time range, and so forth. And then you can set, instead of saying, hey, go get me the data, it'll be, hey, generate me a script stub to show me how to do this. and boom, here's Python, MATLAB, IDL, whatever you want. It shows you, here's the script you need to get the data that you've selected. And of course, you could go in and modify the time range or whatnot to pull in different data items. So that's super useful. Another thing that Bob Weigel did too. So, okay. So there are multiple other projects. There's a GitHub site where people are contributing things. And then I mentioned the interactive mechanism. We just had a successful session at the Python and Heliophysics Summer School where there was a whole bunch of Jupyter notebooks to go through and explain different problem sets, and then solutions on take data from here, compare it with this data, or find out what this spacecraft was, where it was at this time, and compare it with, you know, some other storm event. So there's some good examples you can work through with that. Okay, and I'll just briefly mention this. One of the hardest aspects still of lots of machine learning projects is that initial data wrangling piece. And if now you have one way of getting to the data, your data cleaning routines can now be very, very similar between one data set and the next. We hired a summer intern this summer and we said, hook up Happy to PyTorch. And, you know, you've got all summer, you know, go for it. And he did it in like 1 week, and we gave him lots of, oh, here's some suggestions, and he's already done most of those. So it's a very simple way to get to from time series data to a machine learning approach. And he said, oh, I did it for TensorFlow too. So, so that's already in the GitHub site. We just he's faster than our public release process. So, and then on top of that, you'll be able to people can contribute data cleaning routines. All right, so what data is available? I don't want to read this, but you can see the names of the institutions here. And it's not just the US. The AMDA server has a ton of space physics data. They merge heliophysics and planetary in Europe. So there's a lot of planetary, magnetospheric, and heliospheric data sets in there too. University of Iowa, LASP has some solar irradiance data. The SWARM mission is picking it up. And most of these folks implemented it on their own. They read the spec and they're like, oh, that's not too hard. We're kind of doing that already, which was sort of our point. And so they added that onto the side. And their original thing is still there, nothing breaks, but they add this other mechanism. And coming soon, like I said, we're working with the ESA folks. They're going through their public release process. SuperMag is there. It's almost working. Timed GUVI, we're still working on that one. Planetary data for NASA, there's a lot of magnetospheric stuff and plasma. It's a planetary plasma interactions node. They have a lot of relevant data. They're working on that, and we're trying to help them. And of course, Madrigal, that's why I came here, talk to people, see about what's the needs for that. So I'll be meeting with them going forward to try and make some progress there. I should also say that if we don't have this yet, but for small providers, I finished my study, I got this data, I'd like to make it available to people. We're headed towards that, where you'll have a drop-in thing. Just drop this on something on top of your data, and now you can serve it out using Happy. That's a little harder because there's server security issues. Not everybody wants to be doing that. So, but that's future proposal work. We're going to try to make that process easier. In NASA, data eventually goes up and ends up in one of these big archives. For a lot of NSF projects, that's not as clear what you would do with some of that. So there's definitely collaborative proposal opportunities for that. If you have ideas about data system elements and you want to incorporate something like this, talk to me. We've got lots of people who could propose with you to try and make that process easier. Other things that we're looking into, so we can do this for measurement data. What about model data? And so Rebecca's online, and I can already hear her thinking, wait, we do that already at CCMC. And it's like, yes, we know. So we're working with them on that too. We have a proposal to look at that for some model data from APL, the Gamera model. And so if you put that data, say it's too big to download, 20 terabytes per run or something. So you can put it in the cloud, but still in the cloud, you have to access it. You don't want to download it again because that's expensive. But cloud to cloud, maybe you still need an API over the data. So can we do a Happy-like interface over model data in the cloud to enable uniform access to model outputs? And more client tools, easier on-ramp for small data providers. I kind of mentioned that already. Final comment here, we did get approved as a COSPAR endorsed standard for space weather access data. I know this really matters to everybody, but it is nice to have that acknowledgement that, hey, this looks like a good approach. Let's use this. And it's not just the internal people saying it. Other folks have looked at this and said, yeah, we should probably endorse that. So that's the end of my prepared stuff. This is a kind of choose your own adventure thing. If you want me to talk about gory details about what the spec looks like, I've got lots of slides with plenty of words about that, or we can just do Q&A. So, Mike.
Yeah, John, thanks for all the hard work on this. Technical questions and then
Sure.
another suspicion of people that might be worth talking to in the data.
Okay, and I'll repeat your question for the folks online. Go ahead.
So the technical question is, you showed us the simple code and it was like data and meta. Right? And so presumably the data is the array that comes back and meta is the metadata about it. But where does the data doesn't exist, you know, in the time frame that you're talking about, or how can the error codes, how does the user get that kind of information about it?
Right. Like all data systems, if you get nothing, you have to wonder why. So the availability information does not really convey with Happy. That's another proposal we've thought of writing, because if you have a Happy server, you could go and query it for lots of different times and build that availability info. There are large block availability info available at CEDAR. They have this wonderful chart. Every single mission since 1970 to the present, here's what's available. But it doesn't tell you about gaps. So there are error codes that Happy will return. It can say, you requested way too much time. You can't get 10 years of that 60,000 channel data all at once. So you'll get an error code for that. If there just is no data, you'll just get an empty response, which is, there's not an error. It's just like, well, I found no records. So.
And then you're doing the outreach stuff, but one other folks that might be worthwhile to engage with, that I think maybe a fair amount, is some of the NOAA Nestis stuff, especially like the GOES data. And
right. Okay.
Coming in there, that could come in the same, but if I wish, I could actually get it from there.
Right.
All the later GOES is after 12 are not CEDAR, so you got to go very.
Okay. Okay. Oh, and I didn't repeat his original question. He was asking about error codes and what if the data is not there. And then the comment now was check with the NOAA Nestis people. They have data from GOES 12 and beyond or something like that. Mm-hmm. Okay. Yes.
So two things. One was like mentioned at the beginning that you circle dimensional data.
Uh-huh.
So I assume that return data object is not always the same thing per time.
Right.
So if you're asking query for data with 6 dimensions, return a 6-dimensional array or something.
Right.
And then I guess the follow-on is the auto plot you were showing.
Mm-hmm.
Does that have you give it 1-dimensional data, you get it 6-dimensional data. Does it know what to do with that, or does it specify with that, or is that kind of, it has some limited abilities to expect that you get something sensible or not? So.
Right. Okay. So the question was, does it handle multi-dimensional data? The data comes back in different shapes. Answer is yes. So follow-up question is, okay, autoplot gets a 6-dimensional object. What does it do with that? So, well, no, that's fine. What would you do with that? Someone hands you a 6-dimensional object. What do you do with it?
I asked them, well, what do you want me to do with this?
Right. Exactly. So autoplot gives you options. How do you want to slice this? You want to put this versus that versus what? And so there's an interface in autoplot for dealing with that. And as you can see from the spectrogram data here, this is Van Allen probes, RB Spice data. The description of that other dimension, you have energy bins and then intensity in each energy bin. Well, what are those energy ranges for those bins? That's part of the metadata that you get back with Happy, is a description of the bins or centers. Sometimes they just give you the center, sometimes they give you the boundaries of each bin. Happy captures that information. The idea is there's enough metadata in there to make a scientifically useful plot that can be labeled. You know what the fill values are, and you know what the bin ranges are. There's enough data to plot it. but not much else. So that's a good point to mention this because it doesn't really serve the search function. You know, how do I find what data to do that?
I'm part of the IT project.
Okay, we lost the connection again, but we're back.
Hey,
Okay. All right, well, that's all I had. Thank you all. All right. Now we're going to talk about BISAT. Okay, so I'm gonna. All right, so I'm going to be talking about the Python Satellite Data Analysis Toolkit today, or PySat for short. We have a few developers in the room. It's me, Jeff Quincy in the back, Jonathan Smith, and Angeline Burrell is not here. We've been working on PySat for some time now, and it's got a very kind of generalized focus for just working with data science. Now, we have been building a lot of space science features into it because we are all space scientists, and this is kind of our daily driver for working with data and science all the time. But as part of that general focus, we've also applied to be part of NumFocus, which is organization, nonprofit organization that hosts pretty much all the science Python that we use. So Xarray, Pandas, Matplotlib, NumPy, SumPy, Dask. I mean, the list just goes on. So it's all the kind of core packages that people like us in this room are building stuff on, and we're hoping to be part of this wider community, not just have PySat here in space science, but PySat, more out into the world because it's for just kind of general data. So as a bit of a motivation for this kind of generalization, I'm going to start with a little bit of story about the history of recording music, because PySat is actually designed a little bit like this. Yeah, I believe so. Yeah, thanks for checking. All right, so music recording, has been around for about 100 years or so. And when it first started, you would have a bunch of people that would all have to get in one room, and there would only be 1 or 2 microphones, because with the technology at the time, they could only record 1 or 2 tracks. And recording 1 or 2 tracks is actually fine. You can get like the most authentic recordings with a single microphone. By authentic, I mean, if you're standing in the room while those musicians recorded it, and then you listen to it afterwards with 1 mic, it would probably sound the most like you were actually there. The challenge with only doing 1 microphone is that you need everybody there at the same time. And when you do the recording, everybody's got to be, good during the performance. Anybody messes up, you got to scrap the recording and do it again. So that can be very expensive and time consuming. So it's okay if you only got like say 3 or 4 people, but what about like in that middle picture where you got 10 or 15? Maybe the particular musician you want's in New York, another one's in LA and Seattle, Austin. So it's very difficult to, take this kind of scale and take this type of workflow and scale it up. And this is kind of where we are right now with science. If we want to have, say, multiple data sets, you kind of have to get a bunch of scientists all together in a room at a time, everybody to hash things out to kind of build the data flow. And then if you want to, redo it or something, you might need to get all the scientists. Again, it takes a lot of specific effort, and you tend to have more scientists than data sets to try to work with it. And that's just not really scalable hopefully with the amount of data that we're going to be getting in the future. So what did music do? Well, music figured out multi-track recording so they could do more than 1 or 2 tracks at a time. And then they built an entire workflow around it. So this is a music recording console over here. This particular one is actually for recording Dark Side of the Moon in 1973. But anyway, the workflow that they had by then is like the same workflow that they have now. So it works for all kinds of genres and all kinds of processing. So you might just think, if you have a musician, you just stick a microphone in front of the musician and then that's it. Well, you can do that, but that's not typically what happens. There's all kinds of different audio processing and other thing that goes into it, particularly for modern music to get, the best that they can get. There's a lot of stuff that signal has to go through. There's a lot of different equipment that all does different things. All of it works together. So this is 1970s. Then that middle picture, that's just the digital console that's like available today. It's the exact same workflow there. And then the last picture on the right, this is from Apple's, not GarageBand, Logic, thank you. Yeah, and it's the same workflow again, digitally. So it's very, very versatile and useful. So PySat's kind of built on the same kind of way, because here what we want in the future is to be able to have like orchestras of data sources, right? Not just one or two or three or something. And not only that, but in an orchestra, I mean, you have all these different things going on and you have one person in the middle who's kind of directing it all. And that's, you know, when we're looking at a world now where SpaceX is launching tons of thousands of internet satellites, if we could get some, you know, measurements or something on there or that many, we need to be able to have one or a few people be able to effectively manage all these different measurements at once. Okay. So the technical summary is PySat builds upon X-ray and Pandas. So we're building on standard data formats. We're not trying to roll our own to create a versatile data workflow, abstracting away the challenges of all the file and data handling that we all kind of have to suffer with now. And we want to be able to enable robust instrument independent scientific analysis. So you can write some kind of analysis and then later on you apply data to it, or a different data set, or a later different data set. So you don't have to keep writing new code for every different data set that you come across. You can write code once and then throw all kinds of different data at it. And then most importantly, it's all through like a consistent, easy to use interface. So we kind of have two main classes that PySat's built off of. First one's called the PySat instrument. So it's like the analog is the single audio track. So one of the tracks on that whole console. So that's where you get your data, your metadata. You can load by file or by day or ranges of those things. There's all kinds of iteration built functionality built in, like you iterate over a list in Python, where you can iterate over a data set with PySat, or by orbit using the same type of thing, using a for loop. There's all kinds of customization, because science isn't just load data, stick it into a bin and average it or something like that, though that can be an effective technique. A lot of times you may need to load the data and then do stuff to it, right? So this PySat's got a way that you can still have these instrument independent analyses, and on this workflow remain the same, but you can go in and just tweak particular data sets at any stage of the processing. So it's very quite versatile. And then we're working on the constellation object, which is going to be a group of these instrument objects. So we're trying to make it as compatible as possible. So if you have like an instrument code, you can throw a constellation in there and still have it work. We're trying to make it as compatible as possible, just because, you know, constellation having more instruments, it'll end up being more complicated, have more things in there, but we want to be able to have that same type of basic access. So we're building a whole ecosystem here with PySat. PySat is the main thing that folks are supposed to use. It's the way you can, you know, it's the interface to your data, but it's built like on a data plugin system, because we want to support not only the space science data sets, but all kinds of data sets out in the world. I mean, banks got data, insurance companies got data, Google's got data, Apple's got data, everybody's got data, right? Everywhere. So we want PySat to be able to move to those things too. So PySat itself is very general, doesn't have any specific data support in it, but then for all the different places we get data, we built a package and we put all the specifics there. So we have PySat, then we started PySat NASA, right? It hooks up into CEDAR. We've got a number of different methods and routines designed to download and load data from NASA. So we've got a variety of data sets supported in there. PySat CEDAR is the same type of thing. We've got all kinds of different methods and stuff for interacting with CEDAR data, how to download it and things like that. And then we've collected that into like a PySat thing. So then if a new user comes along, they want to add a data set from CEDAR, they already have a lot of different options. I mean, a lot of support to do so. Now, we were just hearing with Happy that there are generalized automated ways to transfer data. Currently, PySat doesn't hook into any of those, because what we would prefer is to have a scientist in the loop when adding the data set. Not just any scientist, really, somebody who's actually been working with the data and is very familiar with it. Because it's kind of like that music analog. If a scientist comes along and says, I want to add my data set to PySat, it doesn't have to be just, you know, download the data and load the data. The instrumentation person or the knowledgeable person can also provide code on how to clean the data, which also goes in with PySat. So users who come along don't need to know all the details to get good data by default. There's also different processing and other options that are there. So whatever the view that person has who has expertise on the data can add that expertise into PySat, so then the rest of the community can benefit from it without explicitly, you know, perhaps knowing that it exists. So we've got, you know, support for NASA, CEDAR, Madrigal, the kind of core things here for ITM. We also have the PySat models, so it's got support for downloading and loading models, and also has a number of analysis tools and stuff working, model data comparisons, interpolations, all kinds of good stuff like that. PySat space weather is for getting space weather indices. So here we go. So all this stuff here on the right, my pointer is so terribly small, so let me do this. All this stuff over here is like data source stuff. this stuff over here is the analysis type stuff. So PySat missions. PySat missions is there. A number of us on the team have been working with instrumentation. So if you want to get an instrument funded, you've got to write a proposal that gets funded. And as part of any instrument proposal, you tend to have to simulate the mission, simulate your instrument, simulate the performance, show you closed science questions, all that kind of good stuff. Well, that's PySat missions. You can specify an orbit. It'll simulate the orbit, propagate it in time. You couple the orbit into models, which we provide support for. And you get densities, temperatures, et cetera, et cetera. Then you can feed that into your instrument code, and the process all goes on. PySat seasons is for seasonal bin averaging. So I'm sure all of you at least one point or another have seen a science paper that's got like a map, longitude, latitude, or longitude local time or something like that with a bunch of bins, throw in a bunch of data for a seasonal analysis. Well, this PySat seasons can do that for any dimensionality of data, all generally. So you can do every single bin average paper like ever using PySat seasons, as long as the data is in PySat. Incubator, we got some stuff that we're working on or was working and we had to pull out for some reason. PySat tutorials is all kinds of different codes, so people coming along know what to do. Demonstration type things. PySat Komodo, we've coupled a little bit into Komodo. Komodo talk is going to be coming up next. All right, so that's kind of PySat itself. And then over here on the right, I have some stuff that goes along with it. This OMMBV is this magnetic basis vector code. I'm going to be talking about that in a separate session. But I've got the icon and the Cosmic 2 stickers up there as well, because the IVM processing for both these missions is built on top of PySat. All the files that are created for IVM and distributed publicly are made with PySat. It's all built on top of PySat, so I can manage the data and metadata and all that stuff more effectively. So I had like 7 instruments I had to write software for, just me. I didn't have enough me to go for all those instruments. So I needed to write something more general with PySat, which is just like an IVM solver. And then for each of these missions, I could go and make a much smaller package that just coupled the specifics of the mission into the general part of the instrumentation. So it's a very powerful type of system. We've also been just finishing up some funding from the Naval Research Lab and DARPA to operationalize PySat. So PySat's now being used over by NRL and some next generation space weather model thing. And PySat's there to help actually load and get all the data together into a common way, into a common purpose. So it could be any purpose that you want, but that's what PySat really makes it kind of easy to do. So PySat's there kind of right over here. It's the main interface. But for this thing, like you may need to load some space weather indices to figure out what's going on in the world. You may need to get some data from NASA. You may need to get some model data, satellite data, and then model data comparisons, all kinds of other things. But PySat's very open and it's designed not to be like a closed thing where you got to do everything PySat. It's you have a task to do. PySat is available to help you do that task and provide an open framework to make it easier for you to do that, not to prevent you from doing whatever stuff that you want. So this particular version of PySat that's coming out next, which will hopefully not be very long, is a point release. So it's not the biggest of releases, but one of the biggest features is improved NetCDF support. So I already mentioned for Icon and Cosmic 2, producing files for both those systems. Well, the Cosmic 2 files go to CEDAR, the Icon files go to CEDAR. They have very different file format standards. And for those missions, I kind of had my own code. Now I've taken that code and I've generalized it and opened it up and made it more accessible. So now it's all in PySat. So you have PySat data and you can just kind of snap out different file formats by telling PySat translate this to that and all kinds of other things. So it's very powerful in general, and you can make completely compliant CEDAR and other files using PySat. I got a variety of performance improvements, improved file parsing. So it might not seem like file name parsing would be much of an issue. But there's all kinds of different standards that are used in space science, and none of them actually typically satisfy a particular standard. Like you might think, oh, it's just fixed width. Well, sometimes they use delimiters, sometimes not. Other ones are delimited file names, but the delimiters aren't used consistently. All kinds of stuff like that. So we got a couple different ways, but we need to be able to know what files are on the system and all kinds of things like that. And we vectorize some meta processing, and there's a lot of quality of life improvements because, as I mentioned, the team uses that as a daily driver. So if there's any kind of rough points or something, we can run into them too. So when we can, we try to spend some time to file those down and make things pretty good. So upcoming releases. So all packages are getting an upgrade. Some have already been released. PySat CDF is, well, just released as in a few weeks ago. It's very fast loading of 1D and 2D CDF file variables. The plan is to extend that to higher dimensionality.
PySat missions that Jeff is leading that one. That one just released as in a few weeks ago. That's where you can generate and propagate orbits using PySat and then couple in all kinds of different stuff. As I said, PySat models, some model stuff. So we've got support now for TiGCM, SAMI2, and DyneOS. DyneOS is a thing that I've been working on. It's data interpolating empirical orthogonal functions, on and on. So we're releasing a whole new thing, and hopefully the PySat main part itself will come out just in the next couple of weeks, and then we'll finish all these out, and then everything is going to be out and hopefully looking pretty good. So far we've got more than 80 plus data sets, like including NASA ICON, all the different instruments on there, because I used to be on the ICON project, space weather indices, models, CNOS, DMSP, Hickamarka, TEC, cosmic data sets. Goovy is a new one that one of the community members actually generating. So that pull request is up. We're very excited by that. Gold, that's obviously not 80 plus data sets. I didn't write them all. I just did some from memory, but we actually have some tools in PySat to tell us how many supported data sets, just so I can do slides like this. So the point of PySat is to make it possible for you to do whatever kind of custom science you want to do, hopefully much easier. Part of that is, as a user, you need good documentation, I think. If you're going to trust your science to somebody else's software, right, you're going to make sure that you've got support. So we've got all kinds of support. So loads of online documentation. Particularly, we're always looking for new data sets. So we go through everything you need to do to add a new instrument, a new data set, all the different options, requirements, et cetera, et cetera. We've got tutorials. This is again on Read the Docs. So we've got tutorials of a variety of different things you can do with PySat. We've got warning boxes, note boxes, example boxes, the more you know type boxes, right? So we've tried to spend time on the formatting and things within the documentation to, have the core, but also make sure you have, the small things off to the side. Every instrument that's supported in PySat has documentation. So this is coming from PySat NASA. So PySat NASA has all the NASA data sources. So if you want to CNOS IBM, you can click on that. It'll tell you about the data set. Each data set comes with like acknowledgements, references, all that type of stuff that you need as the scientist to make sure you can cite it properly as well as use it properly. And then we've also got examples like this is from PySat season. This is a generalized bin average down here. I'm doing IVM, meridional drifts, things like that. And then the code to do it. So in this code, I actually do bin averages of electron density profiles from Cosmic, as well as just one-dimensional ion drifts from IVM, and use the same code to do both that binning. So the only thing that differs is after the result comes out, it's more complicated to print the 2D stuff, plot the 2D stuff, but there we go. All right, so that's kind of a very high level, very quick review for PySat. So it is a pretty comprehensive thing. Like I said, it's intended to make it possible to do whatever you want. It's not supposed to be super close, but it's something that you can incorporate into your workflow to make things easier. We were a participant in the PyHC summer school. So there was a full online tutorial that was done there. It's 2 hours long. So I don't want to recreate that. I don't have that kind of time here either, but it's online via YouTube. So you can go there if you want to check that out. All the Jupyter notebooks we went through are also on GitHub. So everything's up and out there, available and ready for anybody to use. All right, thank you very much. Any questions? Yeah, John. Oh.
Sorry.
No, please go first.
Mine's easy. I was wondering about your dot constellation versus dot instrument. Does it assume that the constellation is made up of clone satellites, or can they be different?
Oh, so okay, just for the online, I'm going to repeat the question. So the question is on the constellation, is it just repetitions of a single instrument, or it can be anything type of, the constellation can be anything. You can just give it a list of instruments and then it'll be like, cool. We have also defined some constellations. So you can say, hey, use this defined constellation and I'll load all that up too. So yeah. Yeah, thanks for the question. John.
Yeah, I got one too. The ability to tweak the instrument data as you're pulling it in to do those custom settings, that gives PySat an interesting opportunity, because eventually that kind of stuff you would like to capture permanently in the data. They're facing this with the ideal version of SolarSoft, where there's some data sets you can only get to through SolarSoft, because that's the only place where the calibration is done. They don't have the calibrated products. So that might be a good proposal for you sometime to say, hey, I want to take the best settings unimprove PySat, and then capture that as products.
Yeah.
Because it's not going to be PySat forever.
Hmm.
Maybe, you know.
Mhm.
And I mean, every software has.
Of course, yeah, no, there's
and so
nothing
having
taken.
it as the data.
Yeah.
Means that archives then can own it.
Yeah.
So, yeah, that's an interesting possibility.
Thanks for the comment. So just for online, the comment was some data sets like at rest aren't complete because there might be some processing and other things that are only in SolarSoft. So if you want that right data, you got to load it up through SolarSoft. And PySat's customization processing ability can make it perhaps easier to define what that workflow is and then also make it not so dependent on PySat. So it's documented. So, you know, PySat might not last forever, most likely will not, but that information can continue to, to exist. Yeah, sure. Oh yeah, I use SolarSoft and I used to use IDL, so, yeah.
The SDO mission.
Yeah, probably not. Yeah, thanks for the comment. Any other comments or questions? All right, thank you. So that's going to conclude the in-person presenter part of the session. Now we do have 2 virtual presenters coming up. So hopefully the internet makes it through this one and doesn't just cut them off, you know, halfway through. So we're going to start. So a little bit of the order. How do we go first? Because it's tutorial and then the spectral methods. But since then we've got Happy, right, as a way to get data. PySat also includes that, but also loading and processing data. And then coming up here is going to be Komodo, which has other features. But one of the main features is all about visualizing data and things like that. So I was trying to have the session order going a little bit like the result order that you might actually employ in real life. Okay, Rebecca, are you there?
Yep, I'm here. You need to enable sharing.
I need to enable sharing, huh?
Yep.
Where would I do that?
News to me. I'm not allowed to host Zoom meetings. I'm a NASA person.
Oh, yeah, this is my first hosting. Julie, do you think you might be able to?
I just checked to see if I could, and I also need the same permission.
And then advanced sharing options. And
oh, there we go. Thank you so much. Thank you. Rebecca, would you like to try again?
Yep.
All right, let's see if I can get this microphone on. Hello? Hello?
I hear it.
All
Do
right,
you
so
see my slides?
the microphone, so hopefully Rebecca's voice actually is audible to the rest of the room and not just me. All right, Rebecca, you should be good. Oh, let me.
Huh? Do you see my slides?
I do. Let me move things so that the rest of the session can see them.
Okay.
All right, you're good.
All right. So I'm Rebecca Ranget, speaking on behalf of the Komodo team. My team members and co-people are listed below. I'm going to talk today about lowering the utilization barrier for heliophysics model outputs. So the QR codes at the bottom corners of the screen are links to the GitHub pages. We have 2. One is the Komodo core GitHub page, which has the core capabilities for Komodo that we build upon. The CCMC's Komodo GitHub page has the model interfaces that I'm going to talk about today, along with a few other features. All right, so here's a good sample of the models that we host at CCMC. And this is just to demonstrate the breadth of the problem that Komodo that we're facing at CCMC. So we have a wide range of models, as you can see here, across all of the domains of heliophysics and space weather. And the problem is twofold. So first of all, we have to have a link between each one of these different model outputs to the users, just so they can get quick look graphics for each model to have an idea of how a particular model run behaved and so on and so forth. So that requires a custom link between each one of these models to their specific visualization. And that's what CCMC visualization is on the website. Behind the scenes, linking between the models is also a problem because it currently requires a custom link between each pair of models. And you can imagine if I actually drew the links on this slide, it would be a pile of spaghetti. It's a mess. So that code behind the scenes is not only a mess, but difficult to maintain, difficult to update, and it's the motivation for this talk. So a previous solution before Komodo was Chameleon, but it was still difficult to maintain. So we have a problem, and we're working on using Komodo as a solution to this problem. So first, let me tell you what Komodo is. So Komodo is built upon the idea of functionalizing data. So before I get into capabilities, let me explain that concept. So here's an example on the top right in the first block of how to functionalize, say, time series data, one-dimensional time series data with this particular function that I wrote. So it takes a one-dimensional array of time values, a string telling it the variable name, some units, and the one-dimensional array of, in this case, density values. And you can do that repeatedly, all pulling it into the same Komodo object, which I'll explain in a moment. But this Komodo object functionalizes the data. Okay, now you can see my pointer. All right, so in this case, I have two density functions, the same units, because that's what I put in here, and it's written in LaTeX, and you can retrieve this via LaTeX, which is one of the interesting capabilities. So now that this data is functionalized, the Komodo core capabilities offer some very powerful options. You can have automatic unit conversion, such as shown in the first line, and this third function here. You can have simple function compositions for calculations, such as shown here and here on the bottom. And you can also have, here we go. You can also have very simple access through interpolation, where you simply, in this case, enter a datetime object, telling it what time it is, what day it is, and you can get the interpolated value for density at that time. Quite simply, there you go. Another interesting and powerful capability with Komodo is the visualization that Russell talked about earlier. And it's all accessible with very simple command here. So there's a large number of default plots, default plot types based on the dimensionality of the input functions. And they all produce similarly interactive plots, which are based on Plotly. You can click on the variables here to turn them on or off in the plot. You can mouse hover to get some information. You can zoom, you can pan, all these kinds of things. And this interactability can also be saved for future interactability capability later. Okay, that's a mouthful. So this is quite useful for model data comparisons and a couple other things I'm going to talk about later. All of this code is open source and on GitHub with the links here on the slide and the QR codes on the first slide. So now we're using Komodo at CCMC to functionalize the model data so that we can offer our users the same capabilities, but with model data, which is going to be a very powerful solution to our problem. So in order to do this, we're building a network of model readers. And the task here is for each model reader to provide users a direct interface to the model data desired, but all in with identical syntax. So think of this as our pre-happy interface that we're working on. All right, so the syntax is quite simple. You figure out what model string you want based on what's already available in the Komodo library. Retrieve that reader with this syntax, and then execute the reader by just telling it where the data is and what variables you want. And the variable list is optional, just like it's optional with happy. So we're developing this in keeping happy in mind as a future goal. Okay, and with these two simple commands, the model data is functionalized just as it was on the last slide. Now, the point here is that the syntax here for GitHub, as an example, is identical to the syntax for AMGeo, which is identical to the syntax for all of the model readers that we're developing. That's the power behind the solution here. It's identical capability for all of the models. And notice if right here, this little message, in case you ask for a variable that isn't there, it won't break on you and give you some garbled cook, right? It gives you a simple message and then continues on with what it can do. So all of these model readers handle all of the details behind the scenes that typically takes a graduate level or higher research project to get done, right? So the model readers handle all of the custom file formats that come out of these models, all of the grids, all of the interpolations. We take it all behind the scenes. And we give the user a Komodo object with functionalized model data that has the same capabilities as I showed on the previous slide. Okay. All right, take a quick glimpse behind the scenes. So for most of our models, a standard interpolator from the SciPy library is acceptable. However, some models require specialized interpolators such as SWMF, and they're typically written in other languages to get advantageous speeds. We simply link to them via the standard cross-language interfaces, such as shown in the slideshow at right. We do the same approach with custom file types. So these model readers, regardless of what language they're written in, are developed in collaboration with model developers or by comparing to previous implementations at CCMC to verify the functionality and the accuracy of the interpolators. Okay, now the satellite fly-through is a very nice capability that's built on top of the network of these model readers. And because it's built on top of that network, it's also model agnostic. It executes in the same exact syntax as with any other model. You choose the model string, you tell it where the data is, and then the rest of the variables depend upon what version of the fly-through that you use. And I'll talk about those versions in a moment. But notice the different coordinates that you can enter in. So all of the coordinate conversions, whether from a standard one in SpacePy or AstroPy, or a model-specific one for that particular model, all of those coordinate conversions are handled behind the scenes and automatically. We keep the syntax as simple as possible. A lot of these keywords are optional, and all of the fly-through functions are accessible from the command line for use from other languages. There are a couple different fly-through functions, just different flavors of the same idea, and they all produce the interactive visualizations I'm showing in the video at right. All right, so real flight is the example that you saw on the previous slide, and it offers users the ability to fly a real satellite trajectory through the model data. Model fly-through and MyFlight provide the users a way to fly their own satellite trajectory through the model data, either by direct input or through a file. Fake flight allows users to generate and tweak a sample trajectory to fly through the same model data. And there are even more options coming soon. One particular tool that we've developed in Komodo to particularly support the Geospace Dynamics constellation is the reconstruction tool. It's a new satellite constellation tool that reconstructs what that constellation configuration would see in any pair of dimensions, such as the plots shown here. All right, so this is using GetEm data as an example. So we took the simplest configuration, one satellite, flew it through the model data, and we get this. This is what that one satellite could see, for example, a latitude versus time plot. And this can be done for any pair of coordinates, If you instead construct a constellation with three equidistant satellites, you improve your resolution about what you can see. So you can compare between your different results for the different satellite configurations, and you can compare to what the model data actually shows here. This is currently available for a variety of analysis methods, a variety of slicing capabilities. Ask me more details later if you're interested. And then all of it's built upon the fly-through, so it also has model agnostic syntax. All right, so now I'm shifting gears a little bit. So CCMC partners with Ensemble Consultancy for Komodo development. Ensemble Consultancy works on the Komodo core capabilities, and right now they're focusing on cloud capabilities, such as what's described here on this slide. Right? So what they're working on is a way for users to interact with Komodo interactively, right? So it's not just the command line option that's currently exists. This is creating a Komodo object and interacting with it, but on the cloud and from other languages, such as Fortran, C++, etc. This is going to be very useful for the model coupling, particularly since model codes are typically not written in Python. And one way that they're working on increasing the data speed is to use binary data streaming. They're also working on code-free interfaces. So the one at left is a way for researchers and operational people to build their own custom workflows using functionalities already available in Komodo and those coming soon. The one at right has a commercial perspective on what Komodo can do. So you see trajectory parameters for the International Space Station at the top. You see the GETM data represented here with a two-dimensional plot, and then plotted along with the ISS trajectory here, and then some derived components. So I'm going to show a piece of this tutorial video. You can use the QR code here to get the full video. Right, this video goes fast. So all of the plots are interactive, and you can click here, as I showed you earlier, to add or remove variables into the plots. You can use the slider here instead of any kind of code to choose your altitude. You can manipulate the plots here interactively and look at all sorts of derived variables such as drag coefficients and drag forces that would change the orbital parameters of the ISS. Very powerful tool for commercial, in this case, for commercial use. Right. So shifting gears once more, I'm going to show a couple examples of Komodo in action. So we've partnered with several of the core packages to demonstrate not only interoperability of Komodo with those packages, but also how these packages can be used together to answer a science question. So Komodo's portion in this is to take the satellite trajectory pulled from SpacePy and PySpeedS, take that data and fly the trajectory through the model data, in this case, open GGCM data, and then perform a simple model data comparison with this simple command just like I showed before. Also interactive, just as with the other plots that I showed. Like Russell just said, we already have a Komodo interface with PySet, and now Asher Pembroke has developed a way to connect to SunPy. So now Komodo is interoperable with all of the PyHD core packages. One more application for Komodo is the linking to the other languages. So take, for example, Geodyne. It's an orbit propagator written in Fortran. And because it's written in Fortran, it has only been able to use empirical or very quickly running models to predict what the orbit of a satellite is going to be at the next time step. But we've been using Komodo to, for the first time, pull in physics-based models and their outputs into these comparisons as shown here. So I'm not going to talk too much about this because it's not my work, but Katie is on the line if anyone has particular questions. Let me close with this. I have future plans. In light of open science, we're obviously going to be improving our documentation. Yes, I know it needs improvement. It's on my list. We're also partnering to build open access to compute capabilities next to model data, particularly because model data is huge. It can be quite large in most cases. Particularly at CCMC, we're going to be working on speeding up our fly-through via function composition, speeding up our interpolators using parallelization, and working towards adding happy on top of the fly-through and maybe also the model readers. So John and I will be talking. Komodo core improvements I've already talked about. I'm interested in developing tutorials, particularly using Russell's new orbit propagators in PySet. Excited to pull that in into a Python notebook. Also interested in working out a way to pull in two-line elements as inputs to Komodo's fly-through, along with model data comparison using SunPy. Science applications of Komodo are large and growing. You can also already use it for satellite constellation studies, expanded model data comparisons. You can also use it for ensemble modeling across multiple models, not just outputs from one model, such as the paper published a couple years ago, but across several models now with the capabilities. In the future, we're looking towards model-model interfaces for plug-and-play model coupling. So we invite the model development community and the community at large to make your model data interactive. The models we currently support are listed here. Yes, only a handful, but we have a large number of models in the works And if the data is on my machine, I'm a happy camper. I have coding to do. All right, I'll end there. I have extra slides if people have questions.
Any questions for Rebecca? And I'll do my best to translate them to her. Yes.
So looking at this list of models, I don't know everything on there, but a lot of them look like these kind of large regional or global scale. Are you also interested in like localized things?
Hey, Rebecca, the question is, it looks like from the model list, a lot of them are like global scale. Do you have more localized models?
Or are you interested in that?
Or are you interested in that?
So my first answer would be we're interested in anything you want to put in Komodo. It's an open source code. You don't have to have me sitting next to you to do it. I have tutorials and notebooks and all sorts of things on NASA's Komodo GitHub to walk someone through that process. Is CCMC interested in it? Talk to CCMC. So the first priority is going to be any model data we already host at CCMC or that people are, oh, Katie says yes. So I will just leave it at Katie's answer is yes. She is our official point of contact for Komodo. The first priority is data that's already on my machine. Feel free to add.
Do you have a follow-on or no? Any other questions or comments from the audience? All right, let's thank Rebecca one more time. All right, thanks, Rebecca. And then our last speaker is going to be Julie Barnum from LASP. Oh, look, it's already up.
Hello. So okay, it sounds like everyone can see it. That's good to know.
Yep,
Awesome.
you're ready whenever you are.
Great. Well, hello, everyone, and thanks again to the conveners of the session for inviting me to speak today to you all. I'm Julie Barnum. I work at the Laboratory for Atmospheric and Space Physics, or LASP, which is partnering with the University of Colorado Boulder here in beautiful Boulder, Colorado. And today I'll be talking to you all about the Python and heliophysics community, or more commonly as we call ourselves PyHC, and the various contributions that we've made towards open source software since we started in 2018. So, what was the motivation for PyHC to even become a thing? Before 2018, and we formed as a group and started being a centralized location of all things Python and heliophysics. There were many different Python development projects going on, a lot of them kind of siloed and not necessarily talking one to the other, which led to, a lot of overlapping needs existing, but not a realization that there were those overlapping needs between projects there, as well as, then the potential for creating generic libraries across projects. So at the time that wasn't happening as much unless you happen to already know about the existence of another project and worked with those people, right? Additionally, the projects that existed at the time, there were varying applications of standards, varying stages of developments. There were projects that were, fully fledged, very active user base and so forth, well documented, well tested. And then, of course, as we all know, sometimes you need a tool just to do one thing. So you create a one-off and boom, it's there. And then you don't really maintain it anymore. So there was, a mixture of everything in between going on. And additionally, there was then a lack of organized information about all of this existing code that was out there, which if there had been this, organized information base like we have now with PyHC, that would have solved the above problems much more quickly. And then at the core, just a general need for communication. So thus, knowing all these issues, we created PyHC. It actually started with a small conversation sidebar between Aaron Roberts at NASA, I believe, and then my old boss, Alexandria Ware, if anyone knows her. In any case, our tagline is that we promote and facilitate the use and development of Python for heliophysics. Pretty straightforward. More specifically, our guiding, mission statement is that we facilitate scientific discovery by promoting the use and development of sustainable open source Python software across the solar and space physics community. We work to, improve communication and collaboration between everyone within the Python and heliophysics community. We establish, maintain, and hold our projects to standards that we've agreed upon, And we work to foster interoperability between packages in our community and reproducibility of science with our packages. So as far as the leadership team goes for PyHC, there's the principal investigator for the NASA grant that funds all of our leadership activities. That's me. Woohoo. We also have a tech lead, Sean Polson. He makes everything work nicely behind the scenes on our website and so forth. Our NASA point of contact is Aaron Roberts. And then, of course, we have all the PyHC packages, especially the core project leads that are heavily involved in a lot of our leadership decisions. So as far as regular activities go for the community, we hold approximately bi-weekly telecons every 2 to 3 weeks or so as schedules, holidays, and so forth allows. We have a wide range of topics we talk about during those telecons, project intros, updates, relevant community discussions, and so forth. And everyone is welcome to come to those. They are not closed sessions, and you can find all the information about those and everything else on this slide on our website itself. We also hold yearly AGU sessions. The past few years, they've been virtual with COVID, and they've been mostly poster sessions, but hopefully this year we can get some presentations going on. And then twice yearly, we, at least in theory, meet in person. COVID's kind of changed that. But at these biannual meetings, they're open to anyone who's been, in the Python heliophysics community for a long time, to people who are brand new, to maybe both, and maybe PyHC too. And we do even more in-depth, project updates. We have tutorials and hackathons, so you can actually help contribute to projects in our community. And then, of course, more discussions and so forth. And then one of the newest activities we started implementing as of this year was a PyHC summer school. So we used this for at least this year to introduce the core PyHC packages, as well as a few other highly used PyHC packages in the context of how to leverage them for scientific research. So really get, the science community on board with this open source software and using Python. As far as projects in our community go, they're all organized on our heliopython.org website under the projects tab. We have a total of 69 projects. We have a set of 5 core projects. They have a wide range of functionality in their area, and they all adhere to our PyHC standards. You may recognize some of them, PySat being one of them. There's also PlasmaPy, which is a Python package for plasma physics, SunPy for solar physics, and PySpeedas, which has tools for loading, analysis and plotting of data from various missions and ground magnetometers. There's SpacePy, which is the space science library for Python, has file input, output, and etc. And of course you've seen PySat. And then all the other, 64 projects are still important and good for our community. They're just a bit more focused in the functionality that they, work on. You heard a little bit about Komodo. You also heard about Happy. And then, of course, we have 62 other projects you can take a look at whenever you want. So the domains we cover as far as science goes, kind of sun to mud, really. We have projects working in the solar realm, heliospheric sciences, geospace sciences, magnetosphere, and of course, ionosphere, thermosphere, mesosphere physics. And our software capabilities have a ton of different things that our projects can do. We have people dealing with modeling, Komodo, and so forth, machine learning, plotting, data access like Happy, wrappers for other libraries, and CDF writers, and so forth. And as I'd mentioned before, all of these projects are held to a set of standards that we created and agreed upon, and they are based on the AstroPy standards. I won't go into super detail about all of these here. You can find all of our written up standards with a ton of more information on that on our website itself under documents. But just to say this, there are 15 of them, again, based on AstroPy standards, and they're all, basically just to get people to adhere to the idea of open source software, science, making things, readable, well-tested, and so forth, and easy to use. So now onto the summer school that I mentioned earlier. So the summer school that we held this year was probably our biggest in terms of numbers of people attending, in terms of time spent planning, so forth, all the blood, sweat, and tears. Well, not really the former, but in any case, it's one of the biggest events we've held as a community so far, especially towards pushing people to get using open source software and all of the packages that we offer. So, and a little bit of overview, as I mentioned, this was our inaugural year, the PyHC 2022 Summer School. We held it in partnership with the European Space Agency at the European Space Agency Astronomy Center. That was in beautiful, Madrid, Spain. Arnold Masson was our main point of contact. We wanted to make it really accessible, so we had it be free and open to all grad students, early career scientists, and established scientists wanting to go into Python in the heliophysics and space weather disciplines. It was held that very last week of May. We had some remote participation options on Zoom. We also, as a couple of people have mentioned, Russell mentioned it, we recorded and streamed everything to YouTube. So that's open for everyone to see. You can go and watch all the tutorials. And then we have all of the notebooks used in those tutorials on a GitHub page. If you're curious about that link, just let me know, I can get it to you. And we had a Slack space for people to chat with the presenters for those who had registered. So how we spun the motivation for this and where we really geared this summer school towards was that we wanted people to learn some Python best practices and even more so receive hands-on instructions from experts in our field as they, took a deep dive through tutorials, demos, presentations on the projects into the rich ecosystem of heliophysics Python packages. So fancy sounding. More specifically, the goals though, were of course to expose young researchers, the ones who are, going to be the future of our field, to Python-based and open source heliophysics and space weather software. Specifically, we wanted to introduce the PyC ecosystem and help them understand how to use our core packages, especially, and some other highly used PyC packages in their research, how the packages could help them do their research, and then of course, how do you get them local, and then a bit on how to code well. So the next point was that we wanted to attract more users and developers to PyC. That helps improve, the quality of our code, the activeness of our community within PyC, and really incorporates the community into the development, which then of course helps increase exposure of our projects, and then, getting more and more people interested in open source software, which is, the big push now. The next big goal was to develop a working shared Python heliophysics software environment dubbed HelioCloud. That was created by Brian Thomas and Jeff Bradford at NASA Goddard Space Flight Center. And then lastly, we wanted to, give newcomers in the heliophysics field a bit of a taste of cloud-based research approaches, as the HelioCloud was done, as the name suggests, in the cloud. As far as the agenda for that event went, we started off with AstroPy. We, through Twitter communications, actually, I managed to hunt down someone who could come and present on AstroPy as it is used for heliophysics. And then, of course, we moved through some other core packages, SunPy, PlasmaPy, SpacePy, and then also included some of the smaller, more, concentrated in functionality packages, SolarMock, Speezy, Russell's OMMBB, which I think he might have shown on one of his slides. We had Komodo present and Happy, and so forth. And the way that we had people present on these projects was that we had them do a mix of presentations, mainly just kind of like an intro presentation of, hey, this is what our project does. And then we really did a deep dive into tutorials, leveraging Jupyter notebooks within HelioCloud. Just super quick credit to Brian Thomas for these bullets, but HelioCloud is a stable environment, works out of the box of all the PyHC packages. It's containerized, which implements the default Python environment, and removed the need for anyone, attending to have to figure out dependency conflicts, downloading everything to their local laptop and so forth. It has, a community-based platform, HelioHub, which uses this container, and that's what people would see when they were working with it. And if you're curious to see more on HelioCloud, it is public and open source and hosted on GitLab. So when students logged in to HelioCloud and hopped on, the online cloud server, this is what they would see. So it was all just out of the box, ready, good to go for them. And then if they were to go to the left-hand side and click through, then, all of our tutorials were there and ready to go for them to use. As far as the kind of participants we had at our summer school, we actually had just shy of about 500 people who signed up as interested, from 43 different countries, all across North America, South and Central America, Europe, Asia, Oceania, Middle East, and Africa. During the summer school itself, due to COVID restrictions, we only had about 60 people on site at ESAC, and then anywhere from low hundreds to like 250-ish people were on Zoom throughout the day. And our goal was achieved. Most of the participants were students. The darker blue Over here would be the undergrads. Almost half of our participants, a little over, were grad students. And then, not students anymore as postdocs, but young scientists in the field. So like 3/4 of our people were the young crowd, which is awesome. And the majority had, about 4 years or less of programming experience, almost 3/4 again of them. So we're getting new developers and immediately getting them, instead of going to IDL or something else, into Python, into open source. And in the end, students felt that this was an overwhelmingly successful summer school for us. On these kind of scales, 1 is basically awful and 5 is great. So you can see that most people were really satisfied with the summer school experience, and even better, they would want to recommend a future one to more students. And the students were content with our content. They felt that the summer school overall was pretty relevant, and they were happy with the quality of the content. And even better, people were really pleased with our HelioCloud platform. It performed really well, only a couple minor issues, as can happen when you're trying something out for the first time. Gave them all the shared environments any installations already needed. And yeah, students agreed with our analysis of that and said that, it was overall fairly easy to use HelioCloud, just a couple people have problems. And some are even curious to use it in, their future research. So I won't go through all of these a lot, but it was just, nice to get some validation. People, knew that there were different tools in Python for space physics, but now, they know where to go to look for these tools. They know what the projects are. They got to walk through notebooks, which they felt was great. And it was good to meet the people, behind the code, basically. People thought that HelioCloud was great. So that's awesome, because we're looking to use HelioCloud even more within PyHC. And just in general, which I can relate to, the in-person attendance after 2 years of COVID was really nice. Some next steps, I'm pretty close to being out of time, so I'll just basically say there were several other topics people were interested in, so we're looking to incorporate those as well in a future summer school. For the moment, we're thinking of doing a yearly basis for the next few years, then maybe switch to biannual. Next year in 2023, maybe a virtual summer school, kind of still up in the air, but in 2 years. So get ready. In 2024, we're hoping to do the summer school in Texas during the solar eclipse event. So that'll be exciting. Yeah, may incorporate it with our biannual meetings I'd mentioned earlier, and of course, incorporate feedback from all the students. So here are a bunch of different ways if you want to connect with PyHC that you can. There's our website, which is the one-stop shop for everything PyHC. We have a mailing list that I highly encourage you to join. I post a lot about upcoming telecons, meetings, AGU sessions, what have you. We have a couple different chat rooms that you can use. Our Element chat's a bit more freeform. Helionauts is, its whole own platform. It requires an invite to join, but you should be able to find that by going to the main page. We're on Twitter. And of course, there's always my email if you want to chat with me. So that's all I got. Thank you. Any questions?
Thanks, Julie. All right, anybody, any questions or comments for Julie and PyHC from the audience? No, everybody understood what you said, Julie.
Perfect. I know that mine wasn't exactly a software project one, but I hope it was still entertaining.
Oh, I think it was very useful. All right, thank you very much. Can we have one final round of applause for all the presenters? All right. Well, thank you all for attending. So that's all we have for the planned activities. We're 8 minutes early. So I think it's supposed to be 3:30. So
Thanks, everyone.
bye.
Bye.
Bye.